Hi there, another look at invariant lines with matrices and transformations. Now you may recall last time I was looking at some lines, so I think I had a line which was y equals x line, and I was reflecting things in the line y equals x. And when I say things, I try to reflect a curve, so it's not exactly the same as I had last time. But you can see wherever this curve hits the line, because I'm reflecting it, by definition, it kind of should go something like this. Well, that wasn't very good idea. That's what my, I'll try and do that a bit better there, I'm happy now. That's what my points are when I reflect it. And you'll notice there are 3 points which haven't moved. So these are invariant points. But they happen to kind of go on the line. Not all the line, but part of the line. So we call it an invariant line of points. So although it is an invariant line, it's very particular. It's an invariant line of points. But we're going to, on this one, look at more invariant lines. And the last time I remember also showing you this slide, or this picture, where there are occasions when you get a point and it reflects, and it doesn't stay where it's meant to at all. It goes over there. And this point here goes over here. I could pick this point here. You can see it's going to go there. But you'll notice effectively anywhere on that line I can pick. And when I reflect it, it will stay on the line. It won't be staying in the same place, but it will stay on the line. Now this is a genuine invariant line. Anywhere on the line will stay on the line. It's not just a line of points now. So here's one I've not shown you so far. When I reflect it, it will go over, well, I think about there actually. But you'll see it's on the line. We assume this line carries on forever. So these are invariant lines as opposed to an invariant line of points. Now I want you to see this really, because this is what we are going to need to do to be able to find this invariant lines as opposed to the invariant lines of points. So the invariant lines through the origin, I'm going to start off. This is the simplest version you can start with. You'll notice this went through the origin as well. So what I'm after then is to find something. That's gone, bear with me. Get my pen back. So what I'm after then is I'm trying to find a line which will do this thing. And in the exam, they'll basically give you a matrix. They'll say, using this matrix, find a line through the origin which is invariant. Find the invariant line through the origin for this particular matrix. I suppose what we're looking for is we're looking for some coordinate, which I'm going to call x dash y dash. I'll make them dashes because I've got to do some work with them in a bit. I'm going to times the matrix by my coordinate, and I suppose the original thing has got to sit on the same line. So for that reason, I've got to come back to this idea of the line. The line is y equals mx. Now let's just talk about that. So normally, for instance, let's take this value, this one here. This says y equals 2x. Now notice I know the m here is got a gradient of 2. So if I was to say to you with m equals 2, I could say, well, what will y be when x is 5? Of course, as soon as I know that x is 5, I know the y as well. It's immediately 10. And because I've got an equation, knowing the x gives me the y. The two are linked. That's what it does. So what I do is I essentially say, well, if I know one of them, the x, because I've got an equation, the y is known. That will be mx. And the great thing about this is when I multiply it out, it's still got to be, this is my definition, it's got to be invariant. So it's got to still be on this line. Now look, it looks horrid, but this is basically what we're doing. We've got some point. This is the new point I'm going to get. And it is basically going to be equal to my matrix times by my point on the line. And whatever that is, it says here, I can then sub these two new points, these effectively, back into my line equation. My line equation says it must be equal to y equals mx. So I can use my two new points in the same line to try and find my values of m. So let's bear all that in mind as I do a question. So this says, well, what's it say? It says find the equations of the invariant lines. Well, interestingly, it says find the equations of the invariant lines through the origin for this matrix? Well, I'll do what I said I'd do. I'm going to write x dash, y dash. And I'm going to say times the matrix by my points on the line. Now, remember, it's invariant line through the origin. So I'm able to say, well, my equation therefore is y equals mx. This is going to be my equation. My job is to find the m effectively. That's what I'm after, the m. So I can say x there, because any point. Remember, that was my 5 in my example just now. But once I know my x, my y will be mx. So let's multiply this out. What will I get? I'll get minus 4x on that. And I'll get 1 times the mx, so that's plus mx. And I'll get 3 times the x for that. And I'll get minus 2mx. Now remember what I said. I said this equation holds not only for the original point, but it holds my new point as well. So I can write y dash has got to equal mx dash. Remember, this is my x dash and this is my y dash. This is what I found out. So I'm going to write that in. So what was my y dash? It was 3x minus 2mx. And that is equal to m times by whatever x dash was. And x dash said minus 4x plus mx. So you notice what I've done. This is my x dash, this is my y dash. And I've set them into my equation. Y equals mx. Well, first of all, I want to multiply out that bracket. So I don't like brackets. So I'm going to get rid of that. I reckon minus 4mx plus an m squared x. And what do you get here? Well, notice how many x's I've got. X. They've all got x's. I can divide everything by x. That massively simplified my equation. 3 minus 2m equals minus 4m plus m squared. Oops, I just went off the edge. Plus m squared. Now, rearrange it. Move everything over there. I reckon I get m squared. I reckon if I move that over there, I get minus 6m. The 3, when I move it, becomes a minus 3. So I reckon minus 3. And I should write equals 0 really, but I'm going to write over here. It looks better. And I've got to factorize that. Have I done that right? Is that my... Oh no, I've done it wrong. When that moves over, it becomes a plus 2m. So that will make... Actually, I nearly made a bad mistake there. It's minus 2m there. I hope you spotted that before I did. Yeah, that's a minus 2m moves over, becomes a plus. So that's my... Oh, I'm pleased about that because now I can factorize it. Don't think it would have factorized otherwise. So I get m and m at the front. You can just do it on your calculator if you prefer. I think it's plus 1 minus 3. Yes, it is. So that tells me my m is equal to minus 1 or my m is equal to 3. Now, since this was my initial idea that it was y equals mx, therefore my lines are y equals minus 1x or minus x. And what's the other one? Y equals 3x. So 2 possible lines. And they are the invariant lines for this matrix. So sometimes it doesn't say whether or not it goes to the origin or not. So I suppose we've got to be a little bit careful that there's a potential for there to be an invariant line which is not through the origin. And it does say here, it says a question could, however, ask you to show that an equation of the form of y equals mx plus c is an invariant line. Well, I suppose this is because it can get quite tricky to do these on their own. So I'm basically saying here that's possible. They might say to you y equals mx, in which case you use the the y equals mx scenario. When you do your matrix, we saw just now, you write x and mx. Or they might say it's this one, in which case you do your matrix and you'd write your x. And because of this is x plus c, you write x plus c. But you'll notice there's only one thing to find, really. There's a c to find, there's an m to find. If you've got both of them to find, it's quite tricky. But they might just do it the other way around. So I've done one like this. And they said, show that this is an invariant line for this matrix in the reflection of this. Represented by the matrix. So if that's true, then I suppose what I could do is I could say, well, I kind of know what's going to happen. You see, I've got to say my y dash and my x dash, y dash, sorry, is got to equal my matrix, which is minus 0.6, 0.8, 0.8, 0.6. And I'm going to times that by, well, I said to you last time, x and mx. That's because we wanted to find the m. Or I said it could even be x and x plus c if we want to find the c. But I'm saying to you, I actually know what this equation is. It's x. And because y equals minus a half x, add 3. That's what I write. And if I multiply this out, I get, what do I get? Minus 0.6, let's do this. Minus 0.6x. And 0.8 times that, I reckon, is minus 0.4x, got to times both of them, plus 2.4. It's getting complicated, this. And if I do it the other way round, I get 0.8x. And I get, well, I got minus a half of that, so that's minus 0.3x. And then 0.6 times 1.8 is, 0.6 times 3 is 1.8. So plus 1.8. So it's not very pretty then. Let's tidy that up. What have I got? I reckon it's minus a whole x, which is handy, plus 2.4. And the other one is 0.5x. Again, at least it's nice numbers. Plus 1.8. Let's tidy that up there. So, and it said, basically, show that this is true. Now, remember, y equals a half x plus 3. Well, I suppose, let's do what I did last time. Y dash has got to equal this. And it's got to equal minus a half of my x. Well, I'll write x dash plus 3. That's what my rule says. So if this rule is true, that this is an invariant line, this should now give me this when I substitute the x dash into it. So let's go for it. It's minus a half of, what was my x dash? It was minus x plus 2.4 plus 3. And that gives me plus a half x. A half of 2.4 is 1.2, so that's minus 1.2 plus 3. You know what? This only works, isn't it? That gives me a half x plus 1.8, which is clearly the same as that, which is y equal to y dash. Yeah, it's worked. So there you go. We're going to have a look at a few more of those. You can see there's potential for this to get quite complicated. So we'll do this in a couple of lessons, as I've already said, and I'm hoping that makes sense.